Please pause the video and try this problem. And now let's discuss the problem. Here's a summary of the solution to the problem, and now let's work through the solution step by step. When possible, represent what the question is asking you for with a symbol. This question is asking us for the coefficient of kinetic friction. The symbol for the coefficient of kinetic friction is mu sub k. The direction of the velocity vector indicates the object's direction of motion. The sketch which we were provided implies that the box is moving to the right, so we draw the velocity vector pointing to the right. The problem uses units of meters per second, kilograms, and meters. All of those are SI units. The problem mentions the concepts of mass and friction, and we've seen that those are concepts which fit into the Newton's second law problem-solving framework. But the problem also mentions the concepts of speed and distance, and speed and distance are concepts that do not fit easily into the Newton's second law equations. Instead, the concepts of speed and distance fit easily into the kinematics equations. So it appears that on this problem we will need to use both the Newton's second law problem-solving framework and the kinematics problem-solving framework. Remember, we used the concepts that are mentioned in the problem to determine the problem-solving frameworks that are appropriate for the problem. Now, what type of kinematics do we need to apply for this problem? We will apply general kinematics for this problem. I use the term general kinematics to emphasize that we're not applying projectile motion for this problem. The box is moving in a straight line, so we will apply general one-dimensional kinematics for this problem. Now, what concept forms the connecting link between kinematics and Newton's second law? The one concept that appears in both the Newton's second law equations and the kinematics equations is acceleration. So the connecting link between Newton's second law and kinematics is acceleration. But remember that for Newton's second law problems and for kinematics problems, we need to think in terms of components. Let's use these axes. The box is moving horizontally in the x component. So for this problem, we will apply kinematics only to the x component. So for this problem, the connecting link between kinematics and Newton's second law will be a sub x. The problem is asking us for mu sub k. Mu sub k is part of the equation for the magnitude of the kinetic friction force. And force is a concept that fits into the Newton's second law equations. So we expect to use the Newton's second law equations to determine mu sub k. So now we have a plan for attacking this problem. The plan is use general one-dimensional kinematics to determine a sub x. Then substitute our result for a sub x into the Newton's second law x equation. Then use the Newton's second law equations to determine mu sub k. Now, actually, my personal preference is to set up both the Newton's second law framework and the kinematics framework before determining a sub x. And actually, my preference is to set up the Newton's second law framework before setting up the kinematics framework. So now let's proceed to set up the Newton's second law problem-solving framework for this problem. Remember, if you felt that the setup for the Newton's second law framework was easy, then you can use the table of contents in the progress bar at the bottom of the video to skip ahead to the setup for the kinematics framework. We begin the Newton's second law setup by drawing the free body diagram. The problem mentions the mass of the box, which is a clue that we should focus our free body diagram on the box. We draw the vector for the box's weight, and then we ask, what is touching the box? Well, the box is being touched by the floor. The floor is a type of surface which will exert both a normal force and a frictional force on the box. The box is sliding across the floor, so we apply kinetic friction, not static friction. There's nothing else touching the box besides the floor, so there are no other forces to include in the free body diagram. We use these rules to determine the directions of the forces. Notice that although the box is moving to the right, there are no forces to the right. Now, that does not mean we made a mistake. This is the correct free body diagram. Here's Newton's first law. According to Newton's first law, if an object is already moving and the net force on the object is 0, then the object will continue to move in a straight line with constant speed. So, according to Newton's first law, once an object is moving, no force is required to explain why the object continues to move. In this problem, the box was already moving to the right when the problem began. So according to Newton's first law, no force is required to explain why the box continues to move. Now, of course, in this problem, the box does not experience 0 net force. Because of the leftward frictional force, the box will actually experience a net force to the left. So the box will not move at constant speed. Instead, because of the leftward net force, the box will be slowing down, and eventually, after sliding for 10 meters, the box will stop moving to the right. Another way to put it is that according to Newton's second law, the net force at a particular point in time determines the acceleration at that point in time. The net force at a particular point in time does not determine the velocity at that point in time. So the fact that the velocity is pointing to the right does not mean that any of the forces have to point to the right. Now, let's work on the force table. We begin by representing the magnitudes of the overall force vectors in the first row of our force table. We do have special formulas that we can use to represent the magnitude of the weight force and the magnitude of the kinetic friction force. When we're working with this formula for the magnitude of kinetic friction, we do not have a specific number yet to plug in for mu sub k. After all, mu sub k is what the question is asking us for, and we don't have yet a specific number for the magnitude of the normal force. So we just use this formula itself to represent the magnitude of the overall kinetic friction in the first row of our force table. And since there's no special formula for the magnitude of the normal force, we just represent that magnitude with the symbol lowercase n. The object is moving to the right, so let's choose a positive x-axis that points to the right. Now we can break these forces into components. The normal force is parallel to the y-axis, the weight force is anti-parallel to the y-axis, and the frictional force is anti-parallel to the x-axis, so all three of the forces can be easily broken into components using this rule. For example, the frictional force is pointing in the negative x direction, so the x component of the frictional force is negative. The magnitude of the x component is the same as the overall magnitude, and the y component is 0. When you are representing those components, it's crucial to get these two negative signs correct. Put a plus sign in front of your positive component, and then you'll be more likely to notice those crucial negative signs in front of the negative components. Now, let's begin working on the Newton's second law equations. The box is motionless in the y component, so we can substitute 0 for a sub y. Well, I think this is a good point in our solution to shift gears, and now that we've set up the Newton's second law problem-solving framework, now would be a good point to set up the kinematics framework. Here is a handout which summarizes a systematic method for solving general one-dimensional kinematics problems. You can find a link to this handout in the video description box. I hope that you will now print out this handout so that you can follow along with the steps as we carry them out in this video. Now we're going to apply this systematic step-by-step kinematics process to this problem. Now, if you thought that the kinematics for this problem were simple and straightforward, of course you could use the table of contents in the progress bar to skip ahead in the video, or you could rely more on the solutions documents. But if you thought that this was a challenging problem, then I encourage you to use the systematic step-by-step kinematics process, which we will now demonstrate. Now, there are actually two different types of kinematics which you will use in your introductory physics class. The most typical, most common type of kinematics that you'll use is kinematics with constant acceleration and changing velocity. Occasionally, though, you will also encounter problems where you can use a much simpler type of kinematics that involves constant velocity. So we need to begin by asking which of those types of kinematics applies to this problem. Now, the problem tells us that the box is slowing down. Since the box is slowing down, we know that the velocity is changing. So this is a problem that involves changing velocity, not constant velocity. How about the acceleration? The problem tells us that the box is moving with uniform deceleration, and that information tells us that the box's acceleration is constant. Notice that in physics, the term acceleration is used differently than in everyday language. In physics, the term acceleration can refer to speeding up, or to slowing down, or to changing the object's direction of motion. For example, in this problem, acceleration refers to slowing down. So on this problem, when we say that the acceleration is constant, we mean that the object is slowing down at a constant rate. So this may seem strange, but in physics, deceleration is considered to be a type of acceleration. By the way, even if the problem had not specifically said that the box has uniform deceleration, we would still know that the acceleration is constant because the forces on the box are constant. The upshot is that for this problem, we will apply the type of kinematics that applies when the object's acceleration is constant, but the velocity is changing. That's the typical type of kinematics that we're usually thinking of when we use the term kinematics in an introductory physics course. For a kinematics problem, it's helpful to build as much of the kinematics information from the problem as you can into your sketch. Let's begin by representing the box's path of motion on the sketch. Well, the sketch that we were provided seems to be implying that the object is going to move from here to here. So I'll simply add this rightward pointing arrow to indicate that our path of motion is from this point to the right to this point. Let's label this point in time as t sub 0 and this point in time as t sub 1. In introductory physics, it's customary for most problems to set t sub 0 equal to the number 0. The problem tells us that the box starts from a speed of 10 meters per second. We can use that to figure out v sub 0 x, the x component of the velocity of the box at time 0, and we can build that into the sketch. Here's how to think about that. We've decided that the box is moving to the right. Well, the object's direction of motion is the direction of the velocity vector. To the right is our positive x direction. So we know that the x component of the velocity at time 0 will be positive. Remember that it's a good idea to get into the habit of putting a plus sign in front of positive components, so that you'll notice when you need a negative sign in front of negative components. The object begins with a speed of 10 meters per second. The speed represents the magnitude of the velocity vector. The object is moving to the right, so the magnitude of the x component is the same as the magnitude of the overall velocity, 10 meters per second. Remember to think in terms of components. Because this object is moving only in the x component, we're only expecting to apply kinematics to the x component. So I'm going to be writing down information about the kinematics variables specifically for the x component. Most general one-dimensional kinematics problems involve an object that either begins or ends at rest, in which case either the initial or the final velocity is 0. In this problem, the box slows to a stop, so we can say that the x component of the velocity at time 1 is 0. For any kinematics problem, you should label the initial and final points in time in your sketch. The initial and final points are the 2 points in time that you intend to substitute into your kinematics equation. For this problem, I think it's pretty clear that we intend to substitute t sub 0 and t sub 1 into our kinematics equation, so we label those as our initial and final points. For kinematics problems, you should make an effort to build as much kinematics information as you can into your sketch, as we've demonstrated here. So far, we have completed these steps in our systematic method for general one-dimensional kinematics problems. Now remember, we've decided that we're going to be applying kinematics with constant acceleration and changing velocity. This box on the handout summarizes the kinematics equations for constant acceleration with changing velocity. Notice that there are 3 different kinematics equations. We don't know yet which of these 3 kinematics equations we're going to be using. So we're not ready yet to write down a kinematics equation. So our kinematics setup does not involve yet writing down a kinematics equation. Instead, our kinematics setup involves simply listing the 5 kinematics variables. The kinematics setup is simply a list of the 5 kinematics variables. Since we decided that for this problem we're applying kinematics to the x component, our kinematics setup for this problem is to list the 5 kinematics variables for the x component: delta t, delta x, v initial x, v final x, and a sub x. We've gotten into the habit of arranging our Newton's second law equations in 2 adjacent columns, and I encourage you to write your kinematics setup in a 3rd column, adjacent to the columns for your Newton's second law equations, as I've shown here. Notice that the box is moving only in the x component, so we apply kinematics only to the x component. On the other hand, the box is experiencing forces in both the x and the y components, so we apply Newton's second law to both the x and the y components. These are the kinematics variables when you are applying kinematics with changing velocity and constant acceleration to the x component. Notice that these variables take it for granted that Vx is changing. That's why we need separate variables for V initial x and for V final x. And also notice that these variables take it for granted that a sub x is constant. That's why we only need a single entry for a sub x, which will apply during the entire interval between the initial point and the final point. The question is asking us for mu sub k, which is not a kinematics variable. Which of these kinematics variables do we need to know in order to answer the question? Based on our plan, we need to know a sub x, so we label a sub x with the word need. In your kinematics setup, label the variable that you need to know in order to answer the question. We'll see momentarily why this label is useful. Here are the specific numbers and symbols that we can substitute for our kinematics variables on this problem. We don't have any information about delta t, so I'll continue to use the symbol delta t. What does the symbol delta x stand for? Well, delta x stands for the x component of the displacement. Now the box is being displaced to the right, which is our positive x direction, so we know that the x component of the displacement should be positive. Remember that we want to get into the habit of putting a plus sign in front of positive components. Based on the initial and final points that we've chosen, delta x stands specifically for the displacement between time 0 and time 1. And based on the information that was given in the problem and in the sketch, the object is being displaced 10 meters. So the magnitude of delta x is 10 meters. We already built into our sketch that v initial x is positive 10 meters per second. That's based on the information that was given in the problem that we're starting from a speed of 10 meters per second. We have also built into our sketch that v final x is 0. Remember that that is based on the information given in the problem that the box is slowing to a stop. The problem doesn't give us any direct information about a sub x. Again, a sub x is what we need to figure out. So I will continue to use the symbol a sub x. The key to improving at kinematics is to use this simple kinematics setup, which consists simply of listing the 5 general kinematics variables, and then listing the specific numbers or symbols that you're going to apply for those variables. Remember that we use the force table to organize the data that we're going to substitute into the Newton's second law equations. Well, similarly, we use this simple kinematics setup to organize the kinematics data. At this point, we've now completed these further steps from our systematic kinematics method. At this point in our solution, we have now completed the setup of our Newton's second law problem-solving framework, and now we've also completed the setup for our kinematics framework. And we've arranged those setups in 3 adjacent columns. Now we can proceed to work through those 2 problem-solving frameworks, work through the math for those frameworks to actually solve the problem. Now, which of these 3 columns should we work with first? Well, there are 3 unknowns in the Newton's second law x equation, so that doesn't look like a great equation to work with first. There's only 1 unknown in the Newton's second law y equation, so it looks like we should probably begin our work on this equation. It's easy to solve the Newton's second law y equation for n, and we discovered that n is 392 newtons. Now we take that result and substitute it into the Newton's second law x equation. Once we've made that substitution, we can see that the Newton's second law x equation still contains 2 unknowns, mu sub k and a sub x. So it looks like we're still not ready to proceed further with the Newton's second law x equation. Well, that's no problem because we still have this 3rd column that we can work on. Let's see if we're ready to make any progress with our kinematics column. For the Newton's second law columns, it was helpful to count the number of unknowns. But it turns out that for your kinematics setup, it's more helpful to count the knowns. So we can count that there are 3 kinematics variables that we know the values for: delta x, v initial x, and v final x. Is that enough information for us to be ready to pick a kinematics equation? Well, notice that each of these kinematics equations from the handout contains 4 variables. Since each equation contains 4 variables, we're ready to use an equation when we know values for 3 of the variables. I've summarized that idea at this point in the handout. When you're working with constant acceleration with changing velocity, when you know values for 3 of the kinematics variables in your setup, that's when you're ready to choose a kinematics equation to solve for one of the unknowns. Well, yes, we do know values for 3 of the kinematics variables. So, yes, we are ready to choose a kinematics equation. Which of these 3 kinematics equations should we choose to work with? Well, clearly, we should pick a kinematics equation that involves the 3 variables that we know values for. And we should pick an equation that involves a sub x, because that's what we need to figure out. Now you can see why it was useful to label a sub x with the word need. This label reminded us that a sub x is one of the kinematics variables that we care about for this problem. So, we should choose the kinematics equation that contains these 4 variables. But here's a faster way to pick the equation. On this problem, the one kinematics variable that we don't particularly care about is delta t. So the fastest way to pick the correct kinematics equation is to choose the equation that's missing the variable delta t. So we should pick the kinematics equation that's missing delta t. We pick this equation because it's missing delta t. We're going to use this kinematics equation. V final x squared equals v initial x squared plus 2a sub x delta x. Of course, we're using a kinematics equation for the x component because that's the component that the object is moving in. This is the right kinematics equation to use because this is the equation that involves the 4 kinematics variables that we care about: delta x, v initial x, v final x, and a sub x. Or, a faster way to put it is that this is the correct equation to use because this is the equation that's missing delta t, the one kinematics variable that we don't care about. Remember, you're ready to choose a kinematics equation when you know values for 3 kinematics variables. For v final x, we substitute 0. For v initial x, we substitute 10 meters per second. For a sub x, we continue to use the symbol a sub x. And for delta x, we substitute 10 meters. The kinematics equation now has 1 unknown remaining, a sub x, so we can now use algebra to solve this equation for a sub x. If you handle the algebra correctly, then a sub x will come out to be negative for this problem. Now, of course, at this point in your solution, you should pause to ask yourself whether it makes sense that a sub x came out to be negative. But I'm going to save my discussion of that issue till later in this video, just to avoid breaking up the flow of our solution. So now we've completed this step from our systematic kinematics method. Now we take the value that we've determined for a sub x and we substitute that value in for a sub x in our Newton's second law x equation. Remember that our plan was to use general one-dimensional kinematics to determine a sub x, and then to substitute our result for a sub x into the Newton's second law x equation. And now you can see that we've completed those steps of the plan. The last step of our plan is to use our Newton's second law framework to determine mu sub k. Well, notice that now our Newton's second law x equation now has only one unknown, mu sub k. So we're ready now to solve this equation for mu sub k and to complete our plan. Be careful to handle the negative signs correctly. In this step, we divide both sides of the equation by negative 392. That cancels the negative signs from both sides so that we end up with a positive result. Notice how now we are arranging our work in three adjacent columns. Two columns for the Newton's second law equations, and now a new third column for our kinematics framework. Using this three-column approach helps you to keep your math organized. So I encourage you to try to use this three-column approach in your own work when you're working on Newton's second law problems that also involve one-dimensional kinematics. We're ready now to answer the question. The question is asking us for mu sub k, the coefficient of kinetic friction, so our answer is 0.51. The coefficient of friction is a unitless concept, so we do not include units on this answer. Make sure that you've answered the right question and that you've answered all parts of the question. It was possible that this question could have asked us about the force of kinetic friction, but no, in this particular case, they're asking for the coefficient of kinetic friction. Now let's ask whether our results make sense. This symbol stands for the magnitude of the normal force. Magnitudes can't be negative, so it makes sense that this result is positive. The magnitude of the normal force is 392 newtons, which is equal to the magnitude of the weight force. Does that make sense? Well, on this problem, the weight force is trying to make the box begin moving down through the surface of the floor. To prevent that from happening, the downward weight force has to be canceled by the upward normal force exerted by the floor. So yes, it does make sense that on this problem, the magnitude of the normal force will equal the magnitude of the weight force. In this version of the free body diagram, I've drawn the length of this arrow equal to the length of this arrow to reflect the relationship between those two forces. Now let's ask whether our result for a sub x makes sense. Obviously, we need to check whether it makes sense that a sub x came out to be negative. Well, our negative x direction is to the left, so this negative sign means that a sub x is pointing to the left. Now, a sub y is 0, so that means that the overall acceleration is also pointing to the left. So now I've drawn a vector arrow pointing to the left to represent that the overall acceleration for this problem points to the left. Does that make sense? Well, we can use this rule to interpret our leftward acceleration. In this case, our acceleration is anti-parallel to the velocity. When the acceleration is anti-parallel, pointing in the opposite direction as the velocity, that means that the object is slowing down. Well, that is consistent with the information in the problem. The problem told us that the box is slowing down. So yes, this negative sign makes good sense. Now, this problem illustrates that the acceleration vector does not indicate the object's direction of motion. On this problem, the acceleration points to the left, but that's not because the box is moving to the left. We know that the box is moving to the right. It's not the job of the acceleration vector to indicate the object's direction of motion. That's the job of the velocity vector. For example, on this problem, the velocity points to the right because the box is moving to the right. So what does the acceleration tell you? Well, as we discussed earlier, the acceleration vector tells you whether the object is speeding up or slowing down or changing its direction of motion. We've seen that on this problem, The acceleration vector tells us that the box is slowing down. Does our result for mu sub k make sense? Well, the coefficient of friction is a concept that takes values between 0 and 1. Our result for mu sub k is between 0 and 1, so yes, this result makes sense. Let's do a recap of the key techniques that we used to solve this problem. This is the first problem in this video series where we had to combine the Newton's second law problem-solving framework with a kinematics problem-solving framework. We used a 3-column approach to organize our work, with the Newton's second law equations in 2 adjacent columns, and our work on the kinematics framework in a 3rd adjacent column. And I encourage you to imitate this 3-column approach when you're working on these types of problems. The key to improving on kinematics problems is to use this simple kinematics setup, which consists simply of listing the 5 general kinematics variables, and then underneath that list, writing the specific numbers or symbols that you're going to be applying for those variables for the particular problem that you're working on. We use this simple setup to organize the kinematics data. Notice that on this problem, it was helpful to make a note of which variable from the kinematics setup we need to figure out. We need a sub x, so we can substitute that into the Newton's second law x equation. The problem tells us that the box is slowing to a stop, and that gave us the crucial number 0 to substitute for v final x. The kinematics equations contain 4 variables, so you are ready to choose a kinematics equation when you know values for 3 of the kinematics variables. The quickest way to pick the correct kinematics equation is to ask, which variable do I not care about? On this problem, we did not care much about delta t, so we picked this kinematics equation because this is the equation that does not involve delta t. Now, in our 3-column approach, how did we know which columns to work with first? Well, notice that at this point, this left-hand column equation has 3 unknowns, so this was not the best column to work with first. On the other hand, this column at this point only has 1 unknown, so we could immediately begin solving this middle column for little n. And furthermore, our kinematics setup has 3 knowns. And when you know 3 kinematics variables, that's when you're ready to pick a kinematics equation. So we were also able to start immediately working with our kinematics equation in this column. From our work on the middle column and the right-hand column, we obtained results for n and a sub x. We substituted those results into the equation in the left-hand column, and then at that point, this equation had only 1 unknown, mu sub k, and we were then able to solve the equation in the left-hand column for mu sub k and solve the problem. So you determine what order to work with the columns by counting the unknowns or counting the knowns. Notice that in the Newton's second law equations, it's most useful to count the number of unknowns. On the other hand, in your kinematics column, it's most useful to count the number of knowns. When you know values for 3 kinematics variables, that's when you're ready to pick a kinematics equation. Now, how did we know that we were going to apply both Newton's second law and kinematics for this problem? From the concepts mentioned in the problem. We saw at the beginning that the problem mentioned some concepts that fit into a Newton's second law framework, but the problem also mentioned some concepts that fit into a kinematics framework. That's how we knew that we were going to apply both kinematics and Newton's second law. We say that on this problem we're applying general kinematics because we're not applying projectile motion. We said it was one-dimensional kinematics because the object is moving in a straight line. The connecting link between kinematics and Newton's second law is acceleration. On this problem, we used kinematics to determine a sub x. Then we substituted our result for a sub x into the Newton's second law x equation. Then we used Newton's second law to determine mu sub k, which is what the question was asking us for. For kinematics problems, it's helpful to build as much kinematics information as you can into your sketch. On this problem, we labeled the key points in time, t0 and t1. We indicated the object's velocity at time 0 and time 1, and we labeled the initial and final points that we were planning to substitute into our kinematics equation. Remember that for this problem, we were originally unable to substitute any specific numbers into the special formula for f sub k. That did not cause us any particular difficulty. We simply used the special formula itself to represent the unknown magnitude of the kinetic friction in the first row of the force table, and then we were able to use that mathematical expression to help us represent the components of the kinetic friction. Did you find this video to be helpful? If so, you can support the videos by making a monthly pledge at my Patreon page. You can visit my Patreon page by clicking the link on the screen or by using the link in the video description box. Thank you.